Okay, so hi everyone. So let's continue from where we stopped last time. So just to recap, let me remind you, we mentioned claim 2, which is the following. Let A be a UFD and M a maximal ideal in AY. Then if M is not principal, not generated by a single element, then the intersection of M and A is non-zero. And as a corollary, we get that if we take A to be, okay, so K as usual is an algebraically closed field. And maybe just to remind you, our goal so far was to show that there is a bijection between the points in K2 and the max spec of Kxy. So each point is identified with the maximal ideal of all the polynomials that vanish at AB. So we also had this corollary. If we take A to be Kx, then if M is a maximal ideal in Kxy, okay, so claim 1, which we proved last time, said that a maximal ideal in Kxy cannot be principal. So if M is maximal in Kxy, it is not principal, so the intersection of M and Kx is non-zero. So we did this last time, and we also proved this, so let me just quickly remind you. So why is this matter bijection? So obviously, we already know that all the ideals of this form are maximal, right? Even if K is not algebraically closed. So it is well defined. It's clearly injective, since suppose that A, B, and C, D are mapped to the same ideal, then we already saw that what the constant A minus C is this polynomial minus this one. Both belong to M, so it belongs to M, but M is a proper ideal, so this constant must be 0. Otherwise, it is a unit, and a proper ideal cannot include a unit. So A is C, and similarly, B is D. So the injectivity is clear, and the surjectivity is the more difficult part. So let's see. So suppose take M bar in the max spec of Kxy. Then what can we do? We will use this corollary. We know that if this, okay, so then we can take the intersection with Kx and find the non-zero element there. So in other words, M must contain a univariate, non-zero univariate polynomial in X. And we show that if this P, the intersection, is a non-zero prime ideal in Kx. We did it last time, and we already know what are the prime ideals in Kx. They are the 0 and the polynomials, the linear polynomials. So P is of the form generated by X minus A for some A. In particular, X minus A belongs to P, which is contained in M, so it belongs to M. And by symmetry, we can do the same for Y to get that there is also some constant B in K, such that Y minus B is in M. So both X minus A and Y minus B are contained in M. So the ideal that is generated by these two, the smallest one, which contains both, should be contained in M as well. But But what? But this one, what can we say about it? It is maximal, and this one is proper. So we must have equality. Okay, so is that clear? Good. So there are two things that I need to show. So one thing is to prove claim 2. We didn't prove it last time. We started. So maybe we can start this, and then we will generalize this corollary. So okay, so actually we did all this last time, and we also started a proof of claim 2. So let me remind you quickly. So okay, so A is a UFD and M is a maximal ideal in AY. And we want to show that if M is not principal, then M, this intersection is non-zero. So we will assume that this is 0, and we show that M is a principal. So suppose okay. So what can we do? So first, we know that M is a maximal ideal of AY. So we have a natural projection from AY to the quotient, which is a field. Since this is maximal, say call it L. So this is the simply map each element, each polynomial here to its coset. And okay, so what we did, we know that okay, so we can consider A, the subring, and consider the restriction of phi to A. Then what can we say about this restriction? Okay, so let's check if it's, I claim that it is injective. So let's see which elements are in the kernel. So an element in the kernel, well, obviously it belongs to A, and also it belongs to the kernel of phi, but the kernel of phi is M. So the kernel is the intersection of M and A, which is 0. So this is injective. Okay, that's nice. So questions so far? Good. But now we would like to work with A is a domain, but we would like to work with the field. So consider K, which is the fraction field of A. So, right, so the elements of K are just quotients A over B, where both are elements of A and B belong to A, and B is non-zero. Equivalence classes of A and B, like in when you construct a Q from Z, the same idea. So we would like to extend to find some phi tilde which extends phi. So, okay. So how can we do it?
Like strategy-wise, why are I do that? Like you think about the strategy of both, like
yeah. So we want to show that M is not principal, and we will see in a minute why the ideal of
Usually the distance, right?
It is.
Is.
Yeah. So it will be easier to work with this thing where K is a field and not just A. We will see it. Yeah. So, okay. So, okay. So how can we do it? So, yeah, we have only. So yeah. So right. So it should be from Ky to L, and we know that, well, it should agree with phi, so y should be mapped to phi of y, the coset of y. And if we take some element a over b here in K, then well, you can check that the only thing that can work is this thing, phi of A over phi of B. So, and we just need to check that it works. So once we defined it for the elements of K and for Y, there is only one way to extend it to a homomorphism from Ky to L. And why? Okay, so why it is important for phi of A to be injective? So we don't want phi of B. So phi of A and phi of A and phi of B are elements of the field L. So we can divide as long as phi of B is non-zero. And the fact that phi of A is injective guarantees that if B is non-zero, then phi of B is non-zero. So everything works, and we can get this phi, and we are good. Okay. But you can just check that this definition indeed defines a well-defined phi tilde, which extends AY, extends phi. Okay. Okay, so now we have a phi tilde from KY to L, and what is, given such a ring homomorphism, what is the first thing that we should consider?
Yeah.
The kernel. So what can we say about kernel? So we have phi bar from KY to L. And remember, L is a field. So I claim the following, that the kernel, first, it contains the kernel of phi, which is M, because phi tilde extends phi, so that's clear. And moreover, it is an ideal of the domain, right? The kernel of the ring homomorphism is always an ideal of the domain. And since L is a field, what can we say? Not necessarily. Okay, so the kernel is a prime ideal. Right, so, well, if the quotient ky modulo the kernel is isomorphic, well, okay, the quotient ky modulo the kernel is isomorphic to the image. So if the image is like L or a field, then it is maximal, but in general, it doesn't have to be surjective. So with the one thing that we can say that the image is a domain. So this is a prime ideal. So you can also suppose that the product take A and B here, such that AB belongs to the kernel. Then, since phi tilde is a homomorphism, then yeah, exactly. So this is the product of these two, and both these two belongs to a field. So if the product is zero, then one of them is zero. Exactly. Yeah. So every time, yeah. Good. So the kernel of this homomorphism is always an ideal of this, and if the image, if the right hand side is a field, then it's always prime. Prime ideal where in KY, and it's not, and okay, good. So what can we say about, so prime ideals in KY? Okay, so the kernel is generated by, okay, since the polynomial ring over a field is a PID, it is generated by some f of f, by some f. So every ideal here is principal because K is a field.
Okay.
So in KY, yeah, all the ideals here are principal, and if it is a prime ideal, then what can we say about F? For yeah, and we can assume that it's monic. If not, we can divide by the leading coefficient for some monic irreducible F in KY. Good. And moreover, so the coefficients are in K, but we can multiply F with some constants to clear the denominators, and we get the same ideal, but this time in AY, right? So if it's like y minus half in QY, then it's the same as 2y minus 1. We can always take CF for some constant C, so we can clear the denominators and get a polynomial in AY. And also if, okay, so one more thing, and is primitive. So what is a primitive polynomial? So
like why the way is in progress of generality, like 3 times F.
Replace F with some constant
from A times F, right?
Constant from A times F.
And then how much? It depends what the step is. But generally, it does the same thing, right? Never mind. Okay.
As an ideal in K, Y, they are the same.
Okay.
Yeah. So
F and CF are CF.
Yeah, in QY, the ideal that this is generated by half Y and by Y are the same, right? Because
yeah, but they're not the same as objects in AY, right? Like over A,
right, they are the same as an ideal of here.
Yeah.
But the representative, the generator, can be chosen from A. Yeah, that's what I mean. Yeah, good. And moreover, we can assume that it is primitive. What is primitive? So if we have a polynomial like 2y plus 4, then the coefficients, like 4y squared, if all the coefficients, the GCD of the coefficient is not 1, then we can divide, then the polynomial is not primitive. So if f is not primitive, so there is some GCD of the coefficient, we can divide by this GCD and get a primitive f. So yeah. So we can choose such a representative f. Yeah.
You're looking at the fact that it's one, right? But that f is only one.
Sorry.
One means that it's equal to one, right?
Yeah.
So the moment that you put f in ay, you multiply it by some element in a.
Right. So it is not necessarily longer monic. Right. So here f, the original f was monic. The leading coefficient was 1, but after I played with this f and took this, it is no longer. Maybe it's still, maybe no longer. Right.
Okay. So you take the CF and now.
Good. So far, well.
So as a primitive, sorry.
If not, divide by the GCD of the coefficients. Like if f is 2y plus 4, divide by 2 to get this.
Then I want to explain.
And those do that in a USD?
Yeah.
But not every element has an input. Still you can.
Yeah, all I need the GCD. Yeah, I can. Like just all I need that every coefficient can be factored to irreducible element and take the common reducible elements. This is the GCD. Divide by this one.
Necessarily as an input. Is there no, you define define the polynomial and then it's just a different polynomial as that.
Yeah. Normalizing, like, yeah. Anyway, okay. So far we know that the kernel is generated by f in ay, which is primitive. Now we want to show that the original m is principal. So let's show that m is f. So let G be in M. So M is contained in the kernel, so it is contained in F. The kernel is F. So what can we say? So G is right. F divide G, but where? In KY. Good. So again, take G in M, then it belongs to the ideal that is generated by F, but this ideal is an ideal here. So it divides G, but the quotient is in KY. And okay, but and okay, so if it was in AY, then I'm done because this will show that
F is the principal idea of M. Right.
yeah, okay, so we'll see it anyway. But anyway, the fact that, okay, so what do we have? We have F in AY, primitive. We have G, which is in M. So, okay, so what we have F in AY, primitive. We have G in M. M is a maximal ideal of AY. So G also belongs to AY. But and F divide G, but in KY. Gauss lemma, which usually you usually see it in a ring in abstract algebra, says that in this case, if F is primitive and G is in AY, then actually F divides G also in AY. There are several versions of Gauss lemma, so this is one of them. Okay. Okay, so to finish, so what do we get? We get that every element of M belongs to F. In other words, the ideal M is contained in F, but M is maximal, so we have equality. Okay?
We already knew that M contained in F, right? So it can
Oh, good, good. So, yeah, yeah. So here F is ideal in KY. Good. Which means that this is all the ideal of all the polynomials that are some polynomial in KY times F. And here, this is F in AY. So it's a subset. Good. And we really need Gauss lemma to claim that not only F divides G in KY, but also if you consider this ideal in AY, we still have this division. So G also belongs to the ideal of F as an ideal in AY. Yeah, the good point.
Can you remind what is Gauss?
Yeah, so again, but so we have this is a maximal element in AY, this is an ideal in AY, and since this is maximal and this is proper, we have inclusion. So Gauss lemma, maybe I can update the notes to elaborate a bit, but one of the versions that we will use is exactly this one. Suppose that F is in AY primitive, G in AY, K the fraction field of A, and F divide G in KY, then F divide G in AY. Maybe I will say a bit more if we have time. It's the anyway, and this of course finishes the proof since we showed the Themis principle. Okay. So the last thing before we move to the next topic is, okay, so let me just remind you. So one of the, so in the problem set 0, one of the questions was, what is the relation between, suppose we have a ring R and some ideal I, and the quotient ring R modulo I, then what is the relation between the ideals of R and the ideals of the quotient ring? So do you remember? So there is a correspondence theorem that says that the ideals of the quotient, there is a one-to-one correspondence with the ideals of R such that contains I. All the ideals in R that contain I. And what is the correspondence? So given such J, take its, so if pi is the natural quotient, then pi j, j over I. Right, so given j that contains I, ideal of R, then its image is an ideal of this ring, and in the converse, if you have an ideal of this, then taking its inverse image, then you can show that it is an ideal in R that contains I, and these two are inverse to each other. Moreover, we have some nice properties. So this is also true for prime and maximal ideals. So the prime and or maximal ideals in this ring correspond to the prime or maximal ideals here, which contains I.
What was the assumption on pi? Ignore the term of freedom.
Sorry, what was
What's the assumption? Like check on pi on the function.
Oh, it's just every element is mapped to R plus I.
So there are something in I. There should be some assumption here, right? Yeah, so I not instead the idea so if you can idea, every idea has this corresponding to the ideas in R and ideas in R module Y.
Right. So yeah. So we will use it now. Right. So in a particular example, so okay. So corollary. So let F be an irreducible polynomial. And let CF be the following ring, K XY modulo F. So right, so for example, in class we saw that if Fxy is y squared minus x cubed minus x, then this is an irreducible polynomial, and we can take the quotient. So this is prime, so this is a domain. So this ring is a domain, and its elements are, we think of them as polynomial functions on the curve that defines, right? So over a finite field, it's just a discrete set of points, but say the field is R, then the curve is just this geometric object, and we have the points on the curve that solutions to F equals 0. And now CF is the ring of polynomial functions that are defined on the curve. So if we restrict ourselves only to the points that lie on this curve, then of course if we have two polynomials, F and G, such that G is, let's say G and H, two polynomials such that G is H plus F, then if we only consider the points on F, then G and H are the same, right? As functions, the value of G at AB, it's the value of H at AB plus 0. So if we only consider the restriction to the curve, then such a G and H are the same element. So we consider this ring, identify them to the coset of G. Okay. So then the claim is that the map IF so we have a bijection between the points on the curve and the max spec of this ring. So Okay, so if f is the 0 polynomial, then zf is k2, and cf is just kxy, and we get the previous result. But now, more generally, there is a bijection between the points on the curve and the max spec of this ring, the quotient ring. Again,
What?
so if f was 0, then zf it's the plane, so it's k2, and this one mod 0 is just kxy. So this in particular implies the but more generally we can also consider take f irreducible, some curve, and then the max spec of CF is in bijection with the points on the curve. And again, what is the point AB is mapped to which ideal? Right, but again, in the quotient. So the image of this, the coset of A minus A and the coset of Y minus B. So I think I will, the proof is written in the notes. I think I will skip it. I want to say something about the next topic, but it's really almost the same. The only thing that is, so obviously we will use this correspondence theorem. And the only thing that we need to check that, maybe I'll say it just in words. So take an element in the max spec. So it corresponds to a maximal ideal in kxy, which contains this ideal. So in other words, if it's a maximal, so the maximal ideals here are of the form x minus a, y minus b without the bars. And the fact that this ideal should contain f, in particular, f should belong to this ideal. So the value of f at AB should be 0. So f should be not only in K2, but on the curve. Was too fast. Okay, so again, so say that we take some maximal ideal in CF in this ring. This is a quotient ring. So what is this ideal? It's the image of some J, which is maximal in R and contains I's. In this case, it's the I of M, where M is maximal ideal of this ring, which contains this ideal. So the maximal ideals of this ring are of the form x minus a, y minus b. And the fact that f, the ideal generated by f, is contained in M means that f of AB is 0. So the point AB is actually on the curve. Okay, it was too fast maybe, but
Well defined, like what is the statement?
no, so we need to check that it's well defined, that it is one-to-one, injective and surjective, and it's all in the node. Right. So yeah. So this was the surjectivity. So every element, every maximal ideal here comes from a point on the curve.
Yeah.
Yeah. But yeah. Okay. Okay, so for the next topic, let me just quickly remind you some basic facts from field theory. So suppose we have a field L, then we say that L over K is a field extension if K is a subfield of L. So for example, C over R or R over Q. It's not a quotient, it's a field extension. The notation is or Q square 2. Okay. Or the rational function field. Okay, so these are all field extensions. And we can, whenever we have a field extension, L is, we can consider L as a K vector space over K. So the degree of the extension is just the dimension of L over K as a vector space. So for example, the dimension of C over R is what? 2, right? Because, for example, we have the bases 1 and I. This is a basis for C over R. Okay? But what is the dimension of Cx over C, the field of rational functions over C? Right, since we have like this set is linearly independent. Okay. So we would like, and what is if we have, let's say, x1, x2, rational function in 2 variables, still infinite, but we want to distinguish between these two. Like this is larger in some sense. So, okay. Okay, so suppose we have a field extension L over K and some element A in L. When we say that A is algebraic over K, if P of A is 0 for some non-zero polynomial in Kx. Right, so square root of 2 is algebraic over Q, since it's a root of x squared minus 2. Okay. So the extension is called algebraic if every element in L is algebraic. For each element, we can find the non-zero polynomial over K such that A is the root of this polynomial. And an element which is not algebraic is called transcendental. So for example, in Cx, the field of rational function over C, X is transcendental. So in other words, okay. Oh, and one more comment. It's algebraic if there is some polynomial such a P, and there is, if it is algebraic, there is also a unique P, which is monic of smallest degree, such that P A is 0. This P is called the minimal polynomial of alpha, of A. Okay? Okay. So, okay, as definition, a subset S of L is algebraically dependent over K if there exists a finite subset S1 to Sn and some non-zero polynomial in kx1 to xn, such that p of s1 to sn is 0. So if there is a finite subset such that these elements satisfy some algebraic relation, they are once we substitute in some non-zero polynomial in n variables, we get 0. So, okay, so such S is called algebraically dependent, and otherwise it is called algebraically independent. So for example, so this definition generalizes the concept of linear independence, right? In linear independence, we only consider P, which are homogeneous linear polynomials. So this is some linear combination. But here we allow P to be some polynomial of multivariate of not necessarily linear. So maybe to get an example, okay, so before with this we finish. So this set is algebraically independent over K if and only if these two rings are isomorphic. The ring of polynomials in n variables and this ring are isomorphic. This is almost immediately right because consider the substitution homomorphism, replace each xi with si. Then the fact that this is algebraically independent exactly means that the kernel is trivial.
So how do you think about the algebraic independent? Like there's some dependency in the field.
Like this. So maybe okay. So
dependency, I understand like different. Okay.
So let L be xy mod some, say, this one. So this is a domain. So take its fraction field. So it's a field that extends K. And what can we say about the set X and Y? Is it algebraically independent? Right. For which P? Right. So for P
minus x1 squared.
Right, so this is a polynomial in kx1, x2, non-zero. And once we substitute x and y, then p of xy is 0. Because in L, y squared minus x squared plus 1 is 0. So this is the classic example. So, okay, so we'll continue with this next time. And as I mentioned, the proofs are written with more details in the notes, so you can check them if something is not clear. Okay.